Welcome back. Now we are getting into the interesting part of this course. We are delving into transistors. Yes, you heard me right. Transistors. Okay, so what is a transistor? A transistor is a fundamental semiconductor device that is used to amplify or switch electrical signals and power, and acts as a building block for modern electronic circuits. And I will share a brief video that can also help you understand how to use a transistor. They primarily operate as switches. Now, switches again, or amplifiers, increasing signal strength. Types, there are majorly two types of transistor. There are bipolar junction transistors, and you have the field effect transistors. We will talk about that when we get there. And significance. As tiny as the transistors can be, they are efficient switches. They are the foundation to integrated circuits and many ICs you see. Many transistors can be etched onto a single chip. Operations. How do transistors work? A small voltage or current at one of the terminal, which is known as base or gate, controls a larger current flowing through the other terminal, the collector to emitter or the drain to source. So enough theory, let's get into some practical things about transistor. A little bit more theory anyways. So when you're working with a transistor, of course, this is what a transistor looks like. This is the symbol of a transistor. So you have this side, and this side. This is the collector, name as C. This is the emitter, name as E, and this is the base. This base is where you input your control signal. This base is where you put in your signal. And when a signal comes in, it allows current to flow between the collector, between here and the emitter. So this is a simple BJT, bipolar junction transistor. And this is an NPN version. Follow me closely. This is NPN. What is PNP? PNP in the other way. Okay, we will get there. The difference between NPN and PNP is that in NPN, current flows from the collector down to emitter. This is the direction of current flow for NPN. For PNP, I've reversed the direction of the transistor, but let me redraw the transistor so you understand better. For PNP, current, let me first draw the transistor. The arrow points in, and you have the base, the collector, and the emitter. For PNP, current flows from the emitter to the collector. This is a PNP transistor. PNP transistor. Let's do another differentiation. For NPN, you need a positive going signal, a positive signal to control it at the base, to turn it on. For PNP, you need a negative going signal, to put it on, to use it as a switch. All right, having said that, let's do a little bit of calculation to know how to use a transistor as a switch. So let's get into transistor as a switch now. Let's assume we want to use both NPN and PNP to turn on a light emitting diode. All right, let's go. Let me create a new node. So transistor as a switch. Basically, we want to use this transistor to turn on a light emitting diode. So we put our resistor, don't forget, then the light emitting diode, like this, then the transistor. Follow me closely. This go to your most negative point, or 0 volts. This is your 0 volts, and this goes to your positive point, maybe your battery. Let's assume we are using 5 volts supply for this. So this is a simple diagram of transistor as a switch. So what we have here is that from the 5 volt supply, the transistor receives a flow of current into its base via this resistor R1, and this one is the load. Everything here between the collector and the power supply is the load. So when this one receives a current via the power supply, it turns on the LED, right? If there's no power through here, it turns on off the LED. We're going to simulate this in our circuit simulation. But wait, how do we get the value of R1 and R2? Don't forget, I said earlier in the video about connecting light emitting diode that if your voltage is 5 volts, then it's just good enough to use 220 volts as the resistor for the LED. 220 ohms rather. So I'll just put this at 220 ohms, and we are done with that. Then how do we know the value of R1? Okay, transistors have a relationship between the current flow at the base and the current flow through the collector and emitter. And that relationship is as simple as this. IC, which is the current at the collector, is equal to, there's a factor called HFE. Times IB. Yes, I know you're hearing this for the first time probably. If you've had it before, that's good. IB is the current flowing into the base. IC is the current flowing through the collector. So HFE is like the gain that for which the base current is being multiplied. So the amount of base current that comes in is going to be multiplied by that gain, and we give you the amount of current that is going to flow in the collector. Actually, HFE is most of the time it will be supplied by the data in the data sheets of the transistor you are using. Do you get? All right, so you can always check it in the transistor you are using. So assuming this transistor is BC547. So BC547 is a simple signal transistor. In most cases, they put their HFE as 300, sometimes as high as 800. So let's just stick with 500, or let's stick with 400, that the HFE is 400. Now our LED requires 10 milliamperes to glow properly, at least 10 milliamperes. So I'm going to show you that with the value of the base resistor, you can control how much current is flowing in the collector. But when it's a switch, we want it to turn on fully. We don't want to limit the amount of current that is going through the load. We want it to turn off fully. So IC is 10 milliampere, right? So to get the value of IB will be equal to IC, which is 10, and that's 0.01 over HFE, that's 400. Let's calculate that. (0.01) divided by 400. That will be 0.000025. That will be 0.000025, right? And that will give us that's the same thing as 1, 2, 3, 0.025 milliamperes. Do you get this already? It means that with as low as 0.025 milliamperes, you can turn on a load of maybe 10 ampere, right? That looks amazing. That looks beautiful. So we just need a little current to turn on a larger current at the collector to emitter. Don't worry if you don't understand yet. We are going to demystify this by a lot of examples. So let's go on. How do we now know the value of resistor that we need? There's something I'm forgetting to tell you that I've not mentioned before. There's a voltage drop between here and here, between the base and emitter, and that voltage drop is 0.7 volts. 0.7 volts. We call it VBE. That's V between the base, voltage between the base and emitter. So we'll soon be done with this calculation. But it's LD for you, right? So if the power supply voltage is 5 volts, right? The resistor R1, we don't know its value, but the current that is flowing through it is that we need to flow through it is this 0.025 milliampere. How do we know the value of resistance? But let's bring back our Ohm's law. The value of resistance will be R, just like we calculated for the lead, will be equal to V, the power supply voltage, minus 0.7, the VBE, all over the current, 0.025 or 000. Let's just write all the zeros. This will be equal to 4.3, right? Divided by 0.0000025. And that will give us what? 4.3 divided by 0.00002. 172,000. That's 172K. 172 kilo ohms. That's the highest value of resistance we've used so far in our design so far. Albeit in practical, if you are using a transistor as a switch to switch on a load or from something, do you know what we normally do? We can't use up to this 172K. We can't use up to that. This is easy, so that we want to ensure that the transistor switch on completely. So what we normally do is that we create a table of assumption. So if we are using 5 volts, you are using a small signal transistor like the BC547, the base current, and you want to maybe turn on a LED like this, I can set the base resistor. I can set the base resistor to 47K, 47 kilo ohms, and it will still work. And I can even set it to as low as 10 kilo ohms. And it will still work. You see, when I was telling you that in most designs, the value of the resistors may not be critical. But let's say, for example, okay, I'm using this as a battery charger to control when the battery should start charging or stop charging, right? I'm using this as a battery charger. So what will happen, I have to carefully consider the value of this resistor here so that it can give me enough current to flow through the battery. So let's design a simple battery charger control system. And that's a project there. So we are still going to use transistor as a switch, but let's say that the control is coming from another spot. Sorry about my resistor. And this is where the battery is connected. And this is the battery you want to charge connected in this fashion. Let's assume you are charging a 12-volt battery. This is you have a 15-volt power supply here. And you have your control signal here. Let's assume the control signal is at 5 volts also, not necessarily 15 volts. Something you are using to control it, maybe it's at 5 volts. Now, this battery is rated. We are creating an assumption now. So let's assume that the battery you want to charge is rated 10 amp hour. So if you are close to batteries, you will see that they write their ratings there. 10 amp hour battery, and you want to charge it with maybe, so I can charge faster. You want to charge with maybe like 3 ampere. You need 3 ampere of current flowing through it at a point, 3 ampere, so that in under 3 hours it should be completely charged, right? So of course you have to choose a transistor that can handle all of the 3 amperes at once. Let's say we choose TIP41 transistor. What would that do? Before we continue, let me show you the data sheet of TIP41, and it's quite simple. So I'm just going to switch to my browser, and search for TIP41. So let's go. Let's search for TIP41. TIP41 transistor. All right, I have some information from AI overview. I have TIP41 is the popular TO220 package NPN bipolar junction power transistor. It handles up to 6 ampere continuous current and 100 volts for TIP41C collector emitter voltage, featuring a 65 watt power dissipation. You see that, so you need all those information. So let's see, the maximum current that you can allow to flow through is 6 ampere continuously and 10 ampere peak current. The voltage that you can put through it, if it's ordinary TIP41, is 40 volts. Then there's TIP41A 60 volts, TIP41B 80 volts, and TIP41C 100 volts. Current gain, do you see that? HFE 15 to 75. So I will just stick with 15, the better, or we can stick with 50, somewhere in between, and the rest like that, like that, like that, like that. So that's TIP41. You can download the proper data sheet from any of the data sheet providers. So for example, this carries PDF. So this will give me a data sheet. All right, so that's TIP41 for you. Let's see the images. What does TIP41 looks like? So this is what it looks like. It looks like this. You can see the base, the collector, the emitter. You can see the base, collector, emitter, TIP41, like that. Okay, let's come back to let's go back to our design. So we're in TIP41 and the current gain is around 50, and we want to put 3 ampere of current through this. So what will be the current that will be required by the base to help us pass 3 ampere through the collector successfully? IB will be equal to IC over HFE, and our IC that we want is 3, and our HFE is, we should see 50%. The I required will be 3 divided by 45, 0.06 ampere. 667 ampere. 1, 2, 3. That's a 67 milliampere. 67 MA. So you need 67 milliampere flowing here into the base for you to allow 3 ampere to pass through this battery to charge it up. Do you get that? So you have to choose the value of your resistor to be able to do that. So if you need 67 milliampere, normally we are advised that this value you can multiply it by a constant, maybe by 5 or by 10. But when we get into simulation, we will see that. All right, so the value of resistor that you will put here for the base RB must be equal to the voltage input into the base, which is 5 volts, minus the VBE, between the base and emitter, which is 0.7, then all over the current that you need to flow, 0.067. And that will give you 5 minus 0.7 divided by 0.067. You need 64 ohms. Do you see that? You need a 64 ohms resistor. Now, if you have been learning well, you will discover that this 64 ohm, you may need to calculate how much power that you need for the 64 ohms. So if you still remember your formula, the power is equal to P. Power P is equal to I square R, right? And that would be 0.067 square multiplied by 64. And that will give us 0.28 watts or 0.29 approximately watts approximately. So that means for this resistor, it's advisable to use something like 1 watt resistor here, so you won't blow up your resistor on time. All right, so that's a simple demonstration. That's a simple calculation for transistor as a switch. Now let's get into demonstration. Let's do something in real life. So we have different transistors here. You can see we have TIP120 here. Now TIP120 is a kind of transistor that has a very high gain, as high as 402, even though it's a power transistor. But let's start with our simple NPN transistor. This is an NPN transistor here. I'm going to put 2 batteries here so you understand what we are building. Let's put a 9-volt battery signifying a powerful power source. Then I will add a coin cell at 3 volts to control the base, right? So I need a resistor. I've added 2 resistors. So if you will see the transistor is labeled collector base emitter. So like that. Let me put a switch in between. Don't worry, it's going to get clear. Let's use a push button switch. Let's rotate it. I'm flipping it so for ease of connection. Okay, the flipping did not work. Let's just keep it like this. I need another resistor. Don't worry, by the time I put the circuit together and do everything, you will understand. Let's put it, I'll put it here. Then I need a light emitting diode, a LED, simple LED. Okay, so let's connect everything together from the then to this, and let this go to the base of the transistor. Are you following? Then this one goes to the, this one should go to the collector, the light emitting diode, just like we drew in our calculation. And this one should go to the power supply. Right? So you have that. The emitter goes to ground or negative. So all the negatives must connect together for you to have a functional circuit. And this one also goes to the same negative. Okay, so you have that connected. Let's properly add colors. Let's make the negative lines color black. Color black. And let's make the positive line color red. Let's make the control line color blue. Sorry for that noise if you are hearing it. And let's make the load connection color turquoise. Okay, let's use brown. So you have this circuit. Okay, so I'm trying to show you how how transistor works, right? So from here you have the battery, a power supply, a source that is connected to the positive is connected to a light emitting diode, to a resistor, then to the collector. So the path of current flow is meant to be from the collector through the emitter to ground. But except there's a control voltage that enters through the base, this thing will not turn on. So let's start the simulation. Yeah, and it is on. You can guess why it is on, right? Without having pressed this switch. The circuit is on. Alright, I will tell you why it's on. So in transistors, because of the sensitivity, the little amount of current it needs to turn on. If you leave the baseline floating, sometimes it can get electricity from neighboring static electricity. It can misbehave, it can do anyhow, it can be on. And most times, if you leave it floating, it's always on. So first, let's set the proper value for this. Let's set it, remember I said 10K is good. They will now attach a large resistance to the base that pulls it to ground. This is a very important step, or else you will not have the result that you want for your transistor. So we have another resistor. I can make it, why did you move there? Make it 100 kilo ohms, right? Let's change the color back to blue. Connect it to ground. Like this. So this is to ensure that the transistor base is always connected. So we connected it via this large resistance 100 kilo ohms to ground. So is this for NPN transistor, you have to do this. You have to do this. So 10K, 100K to ground, 1K. Let's move this on 470 ohms, just like we said earlier. So let's run this simulation again now. And the transistor is on again. Okay, something is wrong somewhere. Let's do this. Okay, I think challenge is with the switch. Let's see the switch I selected. Oh, I get. I connected the switch wrongly. Let's rotate it. Alright, so let's test now. Alright, and it's off now. So by the pressing of this push button switch, the LED comes on. So presently we are on transistor the press this button switch. Now this is a very simple beginning, but you can imagine a lot that you will get done using this simple transistor as a switch circuit. Do you get that? I think I should redraw the circuit to make it a little bit more friendly, right? So let's redraw this circuit. Let's delete all of this. This is a single battery, like that. Let's bring in our transistor. Trans. That's my transistor. Let's bring in our resistors. I need two resistors. A LED. Switch. I think that's all the components. So let's draw this circuit now. Let's first draw the power line using red color. So this one goes all the way up and connects to this. This one also connects there. Alright, let's connect the negative line to this one, go all the way downwards and connects to the emitter light. Alright, this one control resistor goes to the base. And this one connects to the light emitting diode. This one goes to the collector. Simple, right? So this is a much simpler circuit than the former one. So let's start simulation. Now you see this light turned on faintly. Let's stop simulation. Do you see that? Let's start simulation. The light turned on faintly. And why is that? Why is that? It's simply because there's no current flow here. If this switch is pressed, you see the light will turn on fully. The light will turn on fully. But if the switch is not pressed, the light turns on faintly. That's telling you that there's a little leakage current flowing into the transistor, which is sufficient for it to turn on. So to prevent that, we need to add the resistor, another resistor to the base of the transistor. What does this resistor do? It creates a pathway to ground or to negative, so that any tiny current, when the transistor is not current conducting, can be dealt with. So, but we have to make the value of this I. If you remember, this arrangement here is looking like a voltage divider already between here and here. So if we make this one 1K and make this one 1K, it will drop the voltage to the base by half. That's not what we intend to do. So we can set this one, don't forget, I say we can set this, the base transistor, we are using 5 volts. Or since we are using 9 volts, we can set it to like 22K. And we can set this to like 100 kilo ohms. The value of the resistor for the LED should be around 470 ohms. 470 ohms. Now, when you play this circuit now, when you start this circuit simulation, that faint on is no longer there. You see, so the transistor is completely switched off. And when I press the button, the light comes on. When I release it, the light goes off. When I press it, the light comes on. When I release it, the light goes off. Let's do that again. So this is a simple transistor as a switch. Now we're going to be doing a lot of projects now that we've gotten into transistor as a switch. We're going to be doing a lot of projects. So brace up, the journey just began.